We've talked about normal forces quite a bit. And so there's a couple of forces that, sometimes the force just always has a certain value. Like the weight of this book, as long as I am close to the surface of the Earth, the weight of this book isn't going to change, right? It's the force of gravity between this book and the Earth. But if I put the book on the table here, we could draw a free body diagram for that book. And what happens to the, let's first talk about normal forces. Here's our book. Here's the table. Free body diagram over here for the book. Draw your free body diagram for the book. Start you off with a simple one. Okay, what do we have? Normal force and the weight. Anything else? No. We okay with that? Normal force and the weight. Because it's a horizontal surface, we don't have a friction force. And we know that the normal force is going to equal the weight, right? Because the book's not accelerating. It's just sitting there at rest. So the acceleration is 0. So we can say sum of the forces is ma. But a is 0, right? It's at rest. And we'll call up our positive direction. So that means the normal force minus the weight is 0. The normal force equals the weight, okay? We knew that, but I just wanted to work through it for you. Now, I'm going to push down on the book. Here's our book. And what should we do? Should we push down on it with some force? I'll just lean on it a little bit. Okay? I'm going to lean on the book a little bit. So draw a free body diagram for the book. We have a normal force. We have the pushing force, and we have the weight of the book. Is that right? Okay. So now let's apply Newton's second law. Sum of the forces has to equal the mass of the book times the acceleration of the book. We'll call up positive. What's the acceleration of the book? 0. Right? It's not going anywhere, right? It's at rest. So we know it's 0. Even if it was moving, it could still be 0, right? As long as there's no acceleration. Right? But as long as it's moving at constant speed in a straight line. But in this case, we know it's 0 because it's not moving. So what do we have? We have normal force minus F push minus the weight is equal to 0. So how does our normal force change? It's bigger now. The table was pushing back with a certain force before, equal to the weight of the book. Now it's pushing back with a bigger force because it's holding up the weight of the book plus what I'm pushing down. So it's maybe hard to imagine how a surface can do that. But I think if you think about what's happening at the molecular level, right, the surface of this table the surface of the table is made up of molecules that are bonded together, and those bonds are like little springs. So even though it feels very rigid, it can still give a little bit. Okay? And what we have is these molecules that are bonded with almost like springs. That's our surface. And so you set an item on top of that surface, like a book. And what happens is the springs stretch a little bit. Okay? I push down, and so that stretching of the molecular bonds causes an upward force, right? A normal force. I push down on it, the bonds get stressed a little bit more, and the normal force increases. And it keeps increasing until I push down so hard the bonds break, right? The table breaks and I fall through. Okay? So that normal force, it kind of reacts. It changes depending on what's happening on top. As we push down harder, it pushes back more because we know we're not going through the surface. So some forces, you can just calculate what they are. Weight equals mg. You can just calculate it as long as we're near the surface of the earth, right? But normal force, you might have to look at the whole. You can't just say normal force equals the weight. Because what if here normal force equals the weight? Now what happened to the normal force acting on the book from the table? It's bigger now, right? Because not only is it the weight of the book, it's the weight of the book plus the mug, right? And so you have to look at the whole situation to figure out the normal force sort of reacts.